Okay, good afternoon, everybody. Today is Monday, August 28th, and we are in our second week. This is our third statics lecture. So we have we're going to talk about chapter 2, the statics of particles. But before we do that, I want to do just a little bit of orienting where we are and where we're going to go. So if you take a look at our Moodle page, the first thing that you'll see is that our schedule shows that today we have a face-to-face or Zoom, and on Wednesday we'll just be Zoom only. There's no particular reason I'm going to be here. It's just we're sort of in between things. We're going to be starting one topic and finishing another topic, and the homework for the first topic for the conversion factors is due Friday. So I want to have a face-to-face meeting on Friday. You don't have to be here, but I want to be available for a face-to-face in case anybody has any trouble. Then a week from today is Labor Day, and then we'll get off next week. We'll get off to a good start again with a face-to-face or Zoom on Wednesday. But then on Friday, it's going to be asynchronous only. So I will not be on campus that day. So I've got the schedule posted up through September 18th, and I'll finish off the rest of it as things start rolling in. So, but as always, you guys always have the choice. You can meet this class however you want, synchronously, asynchronously, face-to-face, or via Zoom. So I shouldn't say the first thing. The next thing I want to show you, and I better go back and share my screen again because I don't think this comes through unless I do this. The next thing is we're going to be getting chapter 2. Chapter 1 in this textbook really doesn't have very much content. It just mentions conversion factors at the end. And so that's why I have the handout that I gave you. But for chapter 2, there is the textbook, and I do have a version of the textbook here online. So if you have a different textbook, yours may be 5% different than this, but the content is still going to be the same. So you can still work with this textbook. And you can see it prints off funnily. I have that first page always comes out like this underscored thing. So, oh, this is not the first. This is 1.6. Okay, this is the end of that. I know I got those two pages mixed up. Okay, so here is chapter 2. And what we're going to start talking about is the statics of particles. And basically, when we talk about the statics of particles, what we're really saying is statics are things that sit still. So in other words, they're not moving. And we're not really necessarily talking about particles, but we do not take into account the shape or space of a particle. We will definitely do that later in further chapters, but in order to begin our discussion, if you have something that has a shape, even if it's a simple shape, and if you push on it here, for example, it may move forward or it may start to rotate depending on the shape and the friction and some other things. So we just look at points in space because points in space don't rotate. So even if we're not looking at truly a point or a particle, we are looking at things that will not rotate. So we're only considering how the forces affect these shapes in terms of the translation or the movement in a straight line. So this brings us to the subject of vectors and operations with vectors. So what a vector is in general, a force is a vector. And in general, a vector is a quantity that has both a magnitude and a direction. And a force meets that definition. So in other words, if we have a particle and we push on it with a force of 50 newtons in this direction, we can be sure that the resulting motion would be in this direction. If, on the other hand, we pushed on it with a 40 Newton force in this direction, the motion would be along the vector, the line of action of that vector. So that's why they have both a magnitude and a direction. All forces are not created equal. And when you add them, for example, if you had a 30 Newton force pushing down and a 30 Newton force pushing up, and they're collinear, in other words, they have the exact same direction, the net force is equal to 0. Okay. So that means that that particle is not going to move. You're just going to squish the particle, but it is never going to go anywhere under these conditions. So what we talk about then is when we talk about forces, in general, Newton's second law tells us, can we see this? There we are. Newton's second law, which we can just refer to as N2, just because we may write it over and over again, tells us that the vector sum of forces is equal to the mass of an object times the acceleration. And we put arrows above them indicating that the force and the acceleration are both vectors and that these will happen in the same direction. For a particle that is not accelerating, for a body, we'll be more general with this, that is not accelerating, that means the velocity is a constant. That means that forces must then, if the acceleration is 0, the forces are equal to 0. It seems like we're going to have a very short discussion, except the fact they can have more than one force. And as long as the summation of forces in any vector direction is equal to 0, the body will not move in that direction. So when we talk about the addition of vectors, also the subtraction, but we start by talking, the authors start by talking about the addition. The addition of vectors, first of all, they use a bolded letter like this. This means vector P. This means vector Q. It's very difficult for me to draw a bolded letter on my piece of paper, so I generally write them like this. So this is just the way that I would notate it. It means exactly the same. So this means vector P, vector Q. When you add or subtract vectors, you need to add not just the magnitude, but the direction. Okay. So in other words, if you have two collinear vectors, P plus Q, the vector sum of that would be P plus Q, and it would be in, like we're talking about Cartesian coordinates, in this case, in the X direction. Okay. So if, on the other hand, P looks like this and Q looks like this, we have to break it down into different coordinates. We have to look at the X piece and the Y piece, and then we have to add those together separately. Now, in your textbook, sorry, what? Oh, it's a plus sign. That's just my bad handwriting. So there you go. So in your textbook, they talk about the quadrilateral method of adding and the triangle method. And I do not want you to do these. And I'll explain why in just a second. We want to use vector notation and vector components. So we can do all of the problems in the textbook, but we're just not going to do them using the quadrilateral method or the triangular method. We're going to use a mathematical method. It's just based on the different directions of a vector. The reason that I do this is really good for visualization. And if we were in a drafting program, I would rely heavily on these methods. But The first thing is that these two only really work in two-dimensional space. And after a short amount of time, we're going to be working with three-dimensional vectors. This is basically the only method that will work, that we can just extend one little thought process and turn two-dimensional analysis into a three-dimensional analysis. So in other words, this has, I would say this has legs, this goes somewhere, this just dead ends. So unless we were drafters, in which case if we were drafting, we would use these. But for engineers, this is the best way to do it. All right, so getting all the way back into our study of trigonometry, you remember that the theorem of Pythagoras says that if you have a right triangle of sides A, B, and a hypotenuse C, that A squared plus B squared equals C squared. And that's because the sine of 90 degrees is equal to 1. The cosine of 90 degrees is equal to 0, right? So what that really tells us is that if we had a right angle relationship between two legs of a triangle, we have a very strict relationship, and that the two perpendicular legs, if A is perpendicular to B, knowing A and B completely, we can use those to completely describe C. So in other words, if we know that A and B are perpendicular to each other, and we know their magnitudes, we can determine not only the magnitude of C, but we can also determine the direction. We can determine what this angle is and what this angle is, given that this angle is 90. If this angle is not 90, we have to use the rule of cosines. So that's why the law of cosines. So we're not gonna do that. We're gonna just stick to things that are perpendicular. And if they don't look perpendicular, we're going to make them perpendicular. And that is the first order of business here when we start talking about adding vectors. All right, what do I mean by that? Well, what I mean is, say you have some random vector P, and you want to describe it. You know that P has a magnitude of 45 newtons. And you know that P is acting upward 30 degrees from the horizontal. And you have another vector, let's call it Q. And Q has a magnitude of 70 newtons. And it is operating, this is 90, it's operating at an overall angle of 135 degrees from the horizontal. How could we find P plus Q? Well, the first thing is the triangular method says we could draw P, and then at the tip of P, we could start the tip of Q, and then we could drop a perpendicular, and we could find that the sum of them would be based on the triangle. However, if we remember from other pieces of math that we can call the horizontal axis X and the vertical axis Y, we can divide P and Q into horizontal and vertical components based on the angle that they make with something, either the horizontal or the vertical, and then we can add the components together. So X to the right is positive, Y up is positive, X to the left is negative, Y down is negative. So if we look at P, we can say, oh, P of X, the X component of P, is going to be equal to 45 newtons. And it's an adjacent to the horizontal, so that's cosine of 30 degrees. And it's positive because it's going to the right. P of Y is 45 newtons times the sine of 30 degrees. And it's also positive because it's going up from the tail to the tip. What about Q? Well, Q is going to the left. So I can use I think about this angle as being 135. If you find the sine of, or the, excuse me, the cosine of 135 degrees, you'll find that that's a negative number. So if you use the absolute angle, you will get the correct sign. Okay, the correct SIGN, not sine and angle. You'll also get the correct sine and cosine. But if you use 135 degrees, you'll get that. Or if you knew this was 90 and this then would be 45 degrees, you could also use the cosine or the sine of 45 degrees and then take it as a negative. But if you use the absolute angle, it'll come out correctly. All right, so Q sub x is going to be this chunk right here. And so that's going to be equal to, just like here, Q, the magnitude of Q, which is 70 newtons, times the cosine of 135 degrees. And Q sub y is going to be equal to 70 newtons times the sine of 135 degrees. All right, so we can write these as numeric values, correct? If I take the cosine of 30 degrees and I multiply that by 45, I get that P sub x is 38. I'm going to leave a couple more decimals here, 38.97 newtons. And put this here, you can see it. P sub y is the sine of 30 degrees multiplied by 45 newtons, which is 22.5 newtons. And you can see both of these are positive, just like this picture indicates, up and to the right. Now, there's a couple of other points about this. One is whenever you have a trig function, unless it's a 0 or a 1 or a 0.5, almost always it's an irrational number. So you'll always get a boatload of decimals when you do this. So if you keep a couple of decimals to the end and then you round off to the proper number of significant figures, it works better than rounding off at this stage. So keep them till after you get done with that. All right, let's take a look at my Q here. My Q sub x, I get the cosine of 135 degrees, which is negative 0.707. And if I multiply that by 70, I get that my Q sub x component is negative 49.497 newtons. And my Q sub y is the sine of 135 degrees. Wait a second. That should also be negative. Where am I getting that? Oh, no, okay. It's this. So we have to do a complementary angle, right? I guess I could do this. Sine is opposite. So that would be over here. So this angle is 180 minus 135, which is 45 degrees. But it's negative. I'm going to have to think this one out. I'm not remembering. That's what is that what I'm doing? Yeah, thank you. That's exactly right. So it's 265 degrees. Thank you. So if I did the sine of 265 degrees, that gives me a negative, was it 135? Wait, 360 minus 135. Yeah, 225. Yeah, how's that? No, it's okay. Great mind. We got to work together to get the answers correct. But if we do a sine of 225, you get a negative 0.707, which makes sense. Multiply that by 70. And there we go. And we get a negative 49.497. So they're both negative. And because it's essentially a 45-degree angle, they're halves, so they're the same length. All right. So what that means is if we take P plus Q, we would add P sub x plus Q sub x. And then separately, we would add P sub y plus Q sub y. So P sub x is 38.97. Q sub x is negative 49.497. And P sub y is 22.5. And Q sub y is 49.497. So if we add these values together, 38.97 minus 49.497, this value is negative 10.527. Like I said, that's way too many decimals. I'm just going to call it 10.5, although it really should be 11. But I'm just going to call it 10.5, and that's newtons. And over here, we get 22.5 minus 49.497, and that is 26.997 negative, which is essentially 27 newtons. So if I were to write this in vector form, physicists tend to write this in careted parentheses and would write it as 10.5, negative 10.5, comma, negative 27 newtons. This is one form that is acceptable. A way to write it with Cartesian coordinates is to use what's called a unit vector. And a unit vector is very much more than what I'm going to tell you what it is right now. But basically, a unit vector is a vector that has a length of 1 in a particular direction. So the unit vector in the x direction is referred to as I, little scrolly I, and the unit vector in the y direction is referred to as j. So if we want to write it that way, we can write it as negative 10.5 I minus 27 j newtons. Okay, so these two are identical. They're just different ways of writing that. This is kind of more common for engineers to write in the IJ format, in unit vector format. So just to think about this, what this really means is we've taken a magnitude of negative 10.5, and we've multiplied it, simply multiplied it with something that has a length of 1. So we've given it a direction without changing the magnitude. Now, once again, there's a lot more to unit vectors, and we'll talk about that later, and you'll talk about it in other classes as well. But just to get us off the ground, to get us up and running, we'll just kind of leave it at that. All right, so here's what this looks like. These are the components. This is the x component of the vector p plus q. This is the y component of the vector p plus q. And this is the vector sum of p plus q. Now, for addition, the commutative property holds. P plus q is equal to q plus p. So it doesn't matter what order you do them in, as long as you break them down into those cardinal directions, or into x component and y component. The associative property also holds if you have 3 vectors. If you have p plus q plus s, p plus q first added to s has the same value as p plus the sum q plus s. Because vector addition or vector operations can get complicated, sometimes it's good to know that you can scoot things around, because sometimes things will fall out nicely if you work with them in a different form. All right, so this is bringing us up to the end of section 2.1, and there are some homework problems at the end of section 2.1, which I want to take a look at because I want to do one of them for you. Over here just a second. Get rid of this, and then you'll see how this all works. Okay, so remember, you always look for the word submit. There it is, right there. Okay, when you, let me pull up, let me share my screen here. Okay. When you click on the submit button, you'll see different problem sets, but you hand all of those problem sets in together. In other words, all the homework for chapter 2 comes in as a single Moodle submission. But here, we are using, the first problem set is section 2 or is number 2.2, 2.6, and 2.9. And as it says, use trig and vector components, not the parallelogram or the triangle rule, which I call the quadrilateral rule, but it's, yeah, still don't use it. Yes.
That's in the book, right?
It is.
So, if we don't have books yet, like, so I haven't ordered my weekly online.
Absolutely. And I'll do it from there. If we do, the first problem set is 2.2, 2.6, and 2.9. And I'll go ahead and do one of those problems from the textbook online so that you'll have it. But then if you use that problem, you don't want to, like I said, you don't want to cherry pick. You want to make sure you use the same problem, the same book for all three problems in the set. So, but yeah, you're good to go. Yeah.
So, like, if we want to use the online one, we have to order.
At some point, I have some that I can loan you. I don't put the whole book up because it violates copyright law. So I can only put up like 10% of the book. So I do it at the beginning because if somebody doesn't have their text, which is so common, nobody has their textbooks at the beginning. I would like to get started, you know, without you having to photocopy stuff. So, but I do have textbooks I can loan to you if you don't want to buy the text. So it is. Yes, absolutely. Absolutely. I'm just scrolling down. I don't know why I'm doing this so slowly. I could just jump ahead, but I started and now here I am. So if you're, that's right, you gotta finish what you start. There you go. So in this textbook, we have problem 2.2, which looks like this problem right up here. It refers to figure 2.2. And so I'm gonna go ahead and do this. And so if you do your homework then from this book, then just make sure you do 2.6 and 2.9 from this book as well. So that's, and it's just to make sure that you get a good spread. It's like, if you do that, you'll just make sure to have all the skills that you need to move forward. So it's an efficiency thing. I really pick through the problems to make sure that, I don't like to do busy work. I don't like to do the same kind of problem 17 times. So it's just better if we are efficient in our work. So let's do problem 2.2. And I'll share from the screen first. All right, so if you're doing it from a different version of the book, it may look a little different. But basically it says two forces are applied to a bracket as shown. Determine, and it says graphically, like I said, no graphically, we're going to do it vector-wise, the magnitude and direction of their resultant. And we're just going to do it using vectors, right? Okay, so let's go ahead and draw a picture, and then we'll come back to the screen. Figure 2.2. Here's another, we're going to draw what's called a free body diagram. The bracket is really not that important. What's important is the magnitude and direction of my two forces. I have an 800-pound force pulling up and to the right at an angle of 60 degrees from the horizontal, and at an angle 35 degrees below the horizontal, I have a force of magnitude 500 pounds. So back to the cam. All right, so I want to find, let's call this vector P and this vector Q, just because why not be consistent? And let's just say we want to find the resultant, which means the vector sum. All right, so the first thing I need to do is to break each of them into components. P, as we can see, is positive in the X direction and positive in the Y direction. So in the X direction, P sub X is 800 pounds times the cosine of 60 degrees. P sub Y is 800 pounds times the sine of 60 degrees. Okay. Q sub X is in the X direction, it's positive, isn't it? Because it's moving to the, it's from here to here, from the tail to the tip moves to the right. So it's a positive 500 pounds times the cosine of 35 degrees. And in the Y direction, it's going down because the tip to the tail moves downward. So that's negative 500 pounds times the sine of 35 degrees. right, so writing the numeric value, p sub x, take the cosine of 60, multiply it by 800, and that gives me a value of 400 pounds. P sub y is the sine of 60 multiplied by 800 pounds. So that value is 692.8 pounds. Q sub x, cosine of 35 degrees, times 500 pounds. So Q sub x is 409.6 pounds. And P sub y is a negative. Take the sine of 35, multiply it by 500, and we get negative 286.8 pounds. Okay, so I just want to make a point here on this. I just did it by quadrant or the direction of the vector. You can also do it like we could have used this. We could have spun that all the way around. So this is 60 and this would be 325 degrees, and we'd still get the correct signs because the sine and the cosine are positive and negative in that quadrant. All right, or negative and positive, I should say. All right, I have my two pieces. I have my P components. So if I call my vector sum R for resultant, R sub x is going to be the sum of these two numbers. So they're 400 plus 409.6, which is 809.6 pounds. R sub y is equal to 692.8, oops, plus a negative 286.8. And so this number is 406 pounds. Okay, so I have the components of the resultant. So I can say vector R then is equal to 809.6, which I should round to 810 in the I direction, plus 406 in the J direction, and then don't forget the units in pounds. Okay. Now, so that's sort of the basics of how you add vectors. If you had 3 vectors, you would do exactly the same thing. If you had 3 forces pulling on that bracket, you would break each of them into X and Y components, add the 3X components, add the 3Y components. Okay. All right. Do you guys have any questions about that? Excellent. All right. Well, ladies and gentlemen, that is it for today, because the rest I would do is just work more of your homework, and then what fun would you have? So we got to do a little. You guys are good with that. That's good. Thank you. Thank you. But we'll be good. So Wednesday is Zoom only. And then Friday we'll meet again, because Friday is the day that your homework number 1 is due. So I just want to make sure nobody has any questions or problems. We'll talk a little bit more, extending our conversation into chapter 2, but do take a look at the Moodle page, and there are more videos to watch, which are also on that schedule. So if you take a peek at the Moodle page, you'll see that in addition to lectures for this part, for that we've done in class, you'll also by Wednesday, which is right here, have watched videos 2, 3, 4, and 5. All right. All right. And you guys are good to go. All right. Let's see. All right. I'm going to go ahead and stop recording. End of lecture.